Okay, so new topic for today. We're going to be talking about the chain rule. And I'm sure that y'all all remember the single variable chain rule from Calc 1 classes, I guess it is. Let me skip down to the punchline of where it is. Here's the single variable chain rule as you probably remember it. This is one of the different forms. This is using Newton notation, right? Prime notation to represent derivatives. And it says that G compose F prime evaluated at A is G prime evaluated at F of A times F prime evaluated at A. So, all right, kind of an arbitrary looking rule. But there's a kind of an easy way to think about it, and that is that the derivative of a composition is the product of two individual derivatives. So the composition prime is G prime times F prime. Now, evaluated appropriately. And we'll talk about that, why the F of A, it always confused me when I was in Calc 1 class. Why is there an F of A in the middle here where G prime is evaluated? We'll talk about that in a couple minutes. Okay. But big picture, I want to go back up here to this diagram and talk about a natural way to think about, or I think a very natural way to think about the chain rule. Here's our composition of functions. We've got F here. Now you'll note the way I have this set up. X is the input variable, Y is the output variable. That's how I'm going to set up the variables for this little conversation. Then we've got the function G. Y is the input variable, Z is the output variable. Right? That's, again, that's how I'm choosing to set it up here. Now, of course, because we're composing, the variable that I name the output from F, whatever comes out of F, if we're composing, therefore has to be the thing that goes into G, right? So I have to make this choice here, a single name for the output from F and the input to G, same thing. Okay, so that being said, then the composition, right, takes X as its input, gives Z as its output. Okay, fine. Now this is, what's the deal with the arrows on this picture? Recall, I like to think of the derivative as a factor that relates velocities, right? So F prime, the way F prime shows up on this picture, forget slopes, we're not looking at graphs. How would I draw a graph? Right, I've got three different functions here with different input and output variables. Graph, where? What would I possibly draw? It's not clear what that would mean. But looking at the function F here, the derivative is the factor that I multiply by that input velocity to get that output velocity. Right? There's a temptation to think of it as a fraction. There's a temptation to think, it's this length divided by that length. Let's not do that. Let's think of it as a factor, not a fraction. Okay, so that in mind, analogously then, G prime is the factor that you multiply by that to get this. Right? And the composition prime is the factor that you multiply by that to get that. So now I appeal to your sense of Algebra 1, right? And whatever it is you multiply by that to get that, whatever factor you multiply in this first step, and then subsequently, whatever factor you multiply in this second step, all together, you've multiplied by one factor, and then you multiply by another factor. All together, you've multiplied by the product of those factors. Right? That's how multiplying works. I hope that's clear. Is that satisfying to everybody? That the product of two factors is the accumulation of those two multiplications. Okay. And so that tells you right there how it is we know the factor that you multiply by this to get this. In other words, the way you know the derivative of the composition is the product of the derivative of F and the derivative of G. All right. Now, there's different points of view, different ways to think about the chain rule. This point of view about the chain rule is going to generalize very conveniently for us in a couple of minutes. So if you have a different favorite point of view on the chain rule, fine. That's great. But let's focus on this one for the moment because this will generalize nicely. Okay, now let's talk about the where do you evaluate these derivatives? I mean, I just motivated the idea that G compose F prime is G prime times F prime, right? The product of two factors and all that. So what do we evaluate where? Well, let's think a little bit more carefully about, when you say we have a derivative interpreted as a factor. When I say that F prime is the factor that you multiply by that velocity to get that velocity, what I mean is not just F prime as a function, but F prime evaluated at the input point, right? I mean, the function's being applied at this point A. So if I want to know how input and output velocities relate, I need to talk about the derivative at that same point A. Right? So F prime is evaluated at the same point where F is evaluated. That's A. So this is F prime of A. And now let's talk about, in the composition, when I'm, in my final punchline, when I'm thinking about the composition, input velocity, output velocity, where is the composition being evaluated? The composition is being evaluated at that point, A. That's where the input starts, right? A, by way of this composition, goes to G of F of A. That's the point we're evaluating F. That's the point we're evaluating the composition. Therefore, this is the point we're evaluating the derivative. So this is G compose F prime of A. And now let's play that same game with the G function. The G function, we're talking about that as the input velocity, that as the output velocity, and my input point, you'll notice, is there. It's F of A. Right? G is being evaluated at F of A. F of A is the input point to this function. So since F of A is where G is being evaluated, likewise, F of A is where G prime is being evaluated. So G prime of F of A. So that's why that's in there. And that always confused me when I was learning the chain rule for the first time. But anyway, that's why it is. Is everybody on board? This is all kind of a different point of view of stuff that you already know. But I wanted to lay the groundwork for a certain point of view so that we can generalize it. So now let's do that. Let's generalize this to the multivariable setting. Here's our new diagram. I'm just going to draw, for artistic convenience, I'm going to draw a composition of several functions from R2 to R2. Right? So F, you notice, 2 inputs, 2 outputs. G, 2 inputs, 2 outputs. The composition G compose F, 2 inputs, 2 outputs. Okay, so now again, let's think about, derivatives. How do we think about multivariable derivatives? Now, this is new stuff. This is stuff that we only started talking about less than a week ago. So when I say what is the derivative of this function f at that point, what I'm looking for is a relationship between input velocity, that's velocity in the domain, right, and then the corresponding output velocity in the target. And how do we think of the relationship between these vectors? Well, we have a bunch of different choices. I could call this a directional derivative computed by a certain formula, whatever. Better is to say, I think of these as being related by a linear transformation. Right, we have this thing, we talked about this just yesterday. We have this thing called the derivative transformation, df. That linear transformation applies to this input vector to give this output vector. And sure, these are directional derivatives. The big punchline from last time was that most functions that we're going to deal with, all differentiable functions, directional derivatives are computed as a linear transformation on the input velocity. Okay. So, not exactly a factor, but we can think of the application of a linear transformation is one way that you can think of. That's what you do to this to get to that. Now, how do we shorthand linear transformations. Well, we think of it as multiplying by matrices. So an alternative, a different alternative, I can think of what's the relationship between these vectors? Well, there is a factor, which is the Jacobian matrix. Instead of multiplying by a number that we think of as the derivative, to get from this vector to this vector, we're going to multiply by a matrix that we think of as the derivative. Right? So multiplication by the Jacobian matrix. It's kind of like a factor. It's just not a scalar factor. It's a matrix factor. Okay, so same deal for here is g is a function from R2 to R2. What do we mean by the derivative of g at that point? Well, we mean what is the matrix that you multiply by that vector to get that vector. Right? The Jacobian matrix of g is the factor that you multiply by this to get that. Okay, and likewise for the composition. Looking at this composition, the derivative at this point is the factor that you multiply by that vector to get that vector. So we're going to apply the same reasoning that we did on the previous page, and that is factors multiply. Right? If, what do you do to this vector to get this vector is multiply by Jacobian of f. Having done that, to get to here, you multiply by the Jacobian of g. Altogether, starting with this, ending with that, altogether you've multiplied by a succession of matrices, so you've multiplied by a product of matrices. And so the way you take this input vector, the input to the composition, the way you take that input to the composition velocity and get the output velocity is by multiplying by the product of the two Jacobian matrices. And I've written that down in algebra here, but the punchline's exactly what we just talked about, and that is the Jacobian matrix for the composition is the product of the two individual Jacobian matrices. Now, do be careful with the order that you write these down. It matters very, very much. You have to put the order, again, it's kind of backwards. Remember we had that conversation, we were talking about linear transformations, the way that we write functions. And, the way that matrices multiply is kind of right to left. So if we write, for example, let me zoom in here so I can focus. If we write, sorry, I zoomed in too much. If we want to multiply here by some vector v, right? Notice that having f on the right, not the left, critically on the right, has the Jacobian of f acting first, and then subsequently the Jacobian of g at second. So f first, g second, and note that that is what we had in our scenario up here, right? F is acting first, and G is acting second. G is taking what comes out of F as its input. Okay, so it feels wrong, right? When you write it down with the one that's first on the right, it feels kind of backwards, but it's important that it be that way. All right, everybody comfortable with that? By the way, again, highly non-optional. If you get it in the wrong order, you're going to get a dramatically wrong answer, if any answer at all. So you got to make real careful with that. Okay, by the way, don't forget, multiplication of matrices corresponds to composition of linear transformation. So a different way to think about the chain rule is to think about it as a statement. Instead of multiplication of matrices, multiplication of Jacobian matrices, you can think of it as a composition of derivative transformations. Right? It's arguably more elegant written like this. Look how this rolls off the tongue when we sort of pronounce what this says. This says the derivative transformation of a composition is the composition of the individual derivative transformations. Lovely, right? It's exactly what you would hope would be true. Take your pick. In practice, when you're plugging and chugging, this is probably the more convenient way to have it written down. Okay. Okay, what's evaluated where? Let's go back to the picture. Same deal. The composition is being evaluated at the point A, so the Jacobian of the composition has to be evaluated at the point A. F is evaluated at the point A, so the Jacobian of F evaluated at the point A. G, not being evaluated at A. G's never heard of A. Right? G is being evaluated at the point F of A. So the Jacobian of G is evaluated at the point F of A. So just like in the single variable version, so notice that does show up here. The Jacobian of G, the point being referred to is not A, it's F of A. Okay, just like in single variable. Okay, so let's do an example. Here we have a couple of functions. Function from R2 to R3, followed by a function from R3 to R3. Looking at the composition here, G compose F. Notice, having written G compose F, that means F goes first. Right, again, the order seems kind of backwards. But, heads up. That's careful about that. So F goes first, G goes second. And we would like to know what is the derivative, Jacobian matrix. What's the derivative of this composition? Given certain bits of information noted there. Okay, I'm a big believer in drawing yourself a little roadmap first, just to keep track of what's going on, what's where, and what fits in with what. So, first, F is a function from R2 to R3, and then the output from that then goes into the function G, which is R3 to R3. I'm going to follow the pattern sort of implicit in the statement of this question is I'm going to follow the pattern of variables here. So x1, x2, etc. for the first set of variables, then the y's, then the z's. So I'm going to say these variables are x1 and x2. These variables, y1, y2, y3. And these variables, I guess you could call z1, z2, z3, but they're also the values of the g function, and so I'm going to call them, as I did here, g1, g1, g2, g3. Okay, so notice we are given these Jacobians. We are given, in the statement of the question, that the Jacobian of f is, so for that function there, the Jacobian is that matrix. Recall the Jacobian is made up of a bunch of partial derivatives. Don't forget how the partial derivatives are organized inside of that Jacobian matrix. We talked about that last time. And then let's see, we also are given the Jacobian of G is that matrix. Notice, by the way, F has two input variables. Therefore, the Jacobian of F has two columns. G has three input variables. The Jacobian of G has three columns. Okay. Let's talk about the specific points that we're interested in. This says that 1, 2, that's an x1 and an x2. That's an input to the function f, you notice. So that's in the R2, sort of on the left. The output, 310, is over here. Notice that the Jacobian of f is being evaluated at that given input point as is appropriate. The Jacobian of g is evaluated at f's output point, again, as it should be. Okay, is everybody? So now we've got everything kind of laid out now. What fits with what in what way, and I think it's very helpful to have this sort of a diagram written so that you can keep track of where you are and what you're doing. Okay, so the question asks, what is the Jacobian matrix of the composition? At the point 1, 2, of course, it better be at the point 1, 2. That's the only place that we can evaluate the Jacobian of the composition, is the only point where we have these other individual matrices. Okay. And I'm going to cite this rule up here, that the Jacobian of a composition is the product of the Jacobians. Very importantly, first one on the right, second one on the left. Here it is. Jacobian of the composition is the product of the Jacobians. Those matrices were given on the previous page. Multiply the matrices. There you go. There's the Jacobian of the composition. Okay, that was the second part to the question. The second part to the question is here. What's the value of partial of G3 with respect to X1? Okay, now here's where it's super helpful to have the roadmap, helping you keep track of what's where. Partial of G3 with respect to X1. So notice this says I want to know the partial with respect to the first input variable. And I want to know what is the partial of the third output variable. Well, what this says, first input variable, that means we're looking at the first column. So the left column. Left column of the product matrix. This says we're looking at the third element in that left column. That's that number there. Is that cool? Everybody happy? All right. So chain rule is really it's a very, obviously matrix multiplication is a little bit more complicated than scalar number multiplication, and you got to keep track of the variables and what's where and what are the values of this and etc. But make yourself a roadmap, follow the rules. It's pretty straightforward, really. Okay, I want to give you now a different point of view. This scary-looking formula here. My gosh, look at all those symbols. This is a different way of thinking about the chain rule. And notice it's the same thing that we had on the previous page. This is the Jacobian of the composition. G compose F. That's the Jacobian of G, and that's the Jacobian of F. It's all I've done is expand out these individual Jacobians, and of course these individual Jacobians, each Jacobian is made up of a bunch of partial derivatives. The Jacobian of F is, it's all the partials of all the y variables with respect to all of the x variables, organized in the usual way, right? x1 partials, first column, x2 partials, second column, etc. Within each column, let's look at the x1 partials. First the partial of y1, then the partial of y2, then the partial of y3, etc. All the way on down. Okay, likewise, these are the y's with respect to the x's. These are the z's with respect to the y's. And when you multiply them, you get the z's with respect to the x's. All right. So now let's look at an individual element in here, some arbitrary... some particular, I'm going to pick this one just to have something to point to. Suppose I want to know an individual element in that product Jacobian. How would I compute that element? And that element is all I'm actually interested in. Well, my gosh, wouldn't it be nice to not have to do the whole thing if I don't really have to? If all I'm interested in is that one element, let's not deal with this monstrosity. Right? So a convenient alternative is to say, well, I could take the appropriate row of the left matrix, the appropriate column of the right matrix, and just do that one multiplication, that one dot product to get that one element. And notice that gives me a pretty simple formula to write down. I'm going to have to take the dot product of these partial derivatives in green with these partial derivatives in yellow, and writing that all down, I get this. Here's these various green partials. Here's these corresponding various yellow partials. We've got a bunch of different terms there. This is just the dot product that goes into computing that one single composition partial. Okay, so there's a way to remember this formula I think is really nice and very handy in quite a few instances, and that is to think about, kind of forget about all the matrices and stuff, but let's see, I guess I have to zoom back out to full, okay. So think about what I like to call intermediate variables. Okay, so again, we have this kind of a roadmap of, let's come back over to our picture here. We have the y variables are functions of the x variables, right? The z variables are functions of the y variables. All right, so here's all of our x variables, here's all of our y variables, here's all of our z variables. Now, if I'm interested in the partial derivative of zi with respect to xj, zi is going to be one of those outputs. Xj is one of these inputs. Partial derivative says all these other variables over here I'm going to treat as being constants. Right, I'm going to treat all the other x variables as being constants. I'm going to allow changing just this one variable xj, and I'd like to know when I change that variable xj, how much is this zi variable going to change? Right? The proportion between these input changes and those output changes. Sort of partial derivatives. Well, look, what possible way is it going to be that changes in xj are going to cause changes in zi? And there's certain paths, I like to say, along which these changes can propagate. So, for example, when xj changes, that's going to cause y1 to change by some amount. I mean, y1 is a function of all these variables, including xj, and when I change xj, y1 changes a little bit. I compute the partial of y1 with respect to xj. There is a factor, right? An easy partial derivative that tells you when you change xj, what's the factor that you multiply by to get how much y1 changes. That's the partial of y1 with respect to xj. Which, by the way, you'll notice right there. Okay, so who cares? I don't really care how much y1 changes. I want to know when xj changes, how much does zi change? Well, we've seen that the xj change causes a y1 change, but now I'll point out that, and furthermore, however much y1 changes, that's going to then cause zi to change, because zi is a function of, among other things, y1. Right? So this partial derivative, see right there, right, sort of finishes off this path. So grand total, in terms of how changes propagate along this first path, loosely speaking, right, the product of these partial derivatives tells you how much changes in xj are magnified one step at a time, right, to turn into contributions to changes to zi. Okay, so this path here gives that much contribution to the partial derivative that we're interested in. Now, I say contribution. This is not the whole story, right? Xj's changes do not only cause y1 to change, and therefore this red path changes in zi. That's just one path along which changes can propagate. So there's also that path through y2, right? Xj is going to cause y2 to change by a factor that is the partial derivative. y2 is going to cause zi to change by a factor, which is that partial derivative. So this second term corresponds, you might say, to how much changes propagate along that second path. Or you might say the second term corresponds to how much changes propagate through the y2 intermediate variable. Et cetera, et cetera. The last term there is just talking about changes propagating through the ym variable. So I think it's a very convenient way to think about the chain rule. Now, look, ultimately, if I had to pick one to live my life with, I'm going to have to go with this. I'm a big believer in the idea that you should think of derivatives as linear transformations, or at least matrices, and that factors multiply, and gosh, it's really powerful and all-encompassing. And look how elegant and compact our answer is. That's a really great way to think about the chain rule. But very often, we are, in fact, only interested in one particular partial derivative, and being able to conveniently write down a formula for that one partial derivative, right, by thinking of, what are the various different intermediate variables through which paths can propagate. Awful handy. So let me show you how you'll answer a question with this. Here's the same question, largely, that we answered previously with matrix multiplication. Just wanting to compute that one partial derivative. We can make a roadmap, remind ourselves that, look, the setup was that we had x1 and x2 by way of f. We have y1, y2, and y3 that are functions of the functions of x1 and x2, and then by way of g, we had g1, g2, and g3 that were functions of the y's. We've been asked to compute the partial of g3 with respect to x1. We have 3 intermediate variables. Right? Those are the only immediate variables there are, and so you'll notice that we have then 3 different terms, each one sort of corresponding to one of these intermediate variables. First term, you can see in this product of factors how we're looking at how changes propagate through y1. Here, how changes propagate through y2. Likewise, third one, y3. So instead of writing down a great big matrix formula, including a bunch of information that you ultimately don't need for this specific question, this intermediate variables point of view allows you to write down exactly the tight, bare minimum what you need to get this particular question answered. And then you can pull these individual, there's 6 numbers in here, of course, that you need in order to do this dot product. You can pull those 6 numbers out of the given Jacobian matrices and get the same answer. So, a little bit less to write down. Very convenient. Yeah, everybody good? Okay. But do be careful with one thing, though. There is a tendency to, to over-apply ideas that were written down in single variable calculus classes, sloppy conveniences. Here's one. Y'all remember this point of view on the chain rule. This is the Leibniz form of the chain rule. And it's just so tempting to say, oh yeah, the dy's cancel. Right? Oh, it's so tempting. And there's a point of view by which that's actually valid, right? But what I want to point out is that you cannot just extrapolate from that and say, oh yeah, I'll do the same thing in the multivariable context. In this multivariable context, I have seen this happen on exams, and I keep making a bigger deal out of it every semester, every term. And the occurrence of students doing this on exams is slowly decreasing, right? But nevertheless, it keeps happening that students will write down just this because, after all, the y1's cancel. Right? Well, no. That doesn't work at all. Yeah? Everybody see what's happening there? So, this notation, using fractions, using the notation of fractions to represent derivatives is really problematic. It's oversimplified. And it's just going to get you into trouble if you're not careful with it. Now, let me tell you what's going on here. Ultimately, the point here is that thing and this thing kind of represent different things. You can't cancel them because they're not the same thing. The first one says, okay, I'm going to fiddle with x1, and I want to know what's from that, how much does y1 change? Which is fine, and you can do that. You can say, look, I'm going to change x1 a little bit, and as a result, y1 is going to change. But here's the deal. When you fiddle with x1, y1 is not the only thing to change. y2 will change. y3 will change. So when you write that as a numerator, you're saying, I'm only interested in how much y1 is changing, but I have to recognize that y2 and y3 are changing also. Okay. Now let's look at the one that's in the denominator. That says, what if y1 changes and not y2 and y3? y2 and y3 are not allowed to change. Okay, well that contradicts what came from up here. So these are considering, they're both considering changes in y1, but they're considering changes in y1 under very different conditions. So they're not the same thing. You cannot cancel them. So look, I don't have a better suggestion for how to denote partial derivatives. So this is just a notational awkwardness. It's a notational landmine that you just have to make sure to dance around. Right? Please do not step on the landmine. Okay. All right. Okay. Let's look back to single variable calculus. So, prepare to be bored. Right? Here's a function f. F is x squared. G of x is x cubed. Yawn. Right? Two easy functions. No one's intimidated yet. You could ask how to compose those functions. Okay, yeah, sure. What's the derivative of the composition? Boring, right? And one of the big lessons we talked about today is that the derivative of the composition is the product of the derivatives, and these are easy derivatives to take. The derivative of x cubed is 3x squared. The derivative of x squared is 2x, and you can multiply those, and you get 6x cubed. And of course, that's wrong. Okay, now obviously I was playing fast and loose with the notation, and clearly what I forgot to do is I forgot in this that G prime, that has to be evaluated not at the same point where f is evaluated, but it has to be evaluated at the output from x. So I've got to take this x squared and stick that in to where the x is, like so. Sorry, I'll put that in the wrong spot. So x squared has to go into there, like that. Right? So this 3x squared, it's really 3x squared. Right? This is that business about, it's not g prime of A, it's g prime of f of A in order to make the chain rule work. All right, so this is a good thing to stare at and digest and make sure you're comfortable with what happened here. What was the little landmine that I stepped on, and how did I dance around it there? But now let me show you just a better way to avoid the whole problem in the first place. I claim that even this, there's something kind of bad about how I've got this written down, and that is, let's think about the roadmap. What's the picture here? What's a function of what? Well, I've got these two functions. I've got f, and then I've got g. And what names am I giving to the input variables and output variables? Well, f takes x as its input variable. I don't have a name for its output variable. But the name that I'm using as the input variable for g, also x. Right? So I'm using the same variable to represent the inputs for these two different functions, which I am composing, which means that, in effect, I'm giving the same name to the output from f as the input to f. That's super gauche, right? This is highly confusing. That's the source of this confusion up here that causes us to get a wrong answer when we're, being a little too careless. Okay, so my proposal is just don't confuse variables. This is called confusion of variables. Let's just not do that. So here's the way around it. The question comes to us with f as a function of x, with g as a function of x. there's really no technically a problem yet because these are just dummy variables representing the function. Now I've been asked about the composition. Okay, right? Part of the job in realizing that you want to talk about the composition of the functions and you want to use the chain rule is to realize that now all of a sudden, because we've been asked about the composition, this choice of dummy variable is bad. Right? It's super awkward to think of G as being a function of X. F is a function of X. G needs to be a function of whatever name I give to the output from F, not the input to F. So let's just start all over with that G function. I'm going to make myself a little roadmap here again. So I've got this F function and I've got this G function. I want to leave F as a function of X. But I'm now going to rewrite G not as a function of X. That's super confusing, totally inappropriate in this context. I'm going to rewrite G as a function of Y. Right, let's think of it. It's the same function, just a dummy variable telling me what the function G is doing. It's taking whatever input I give it, it's cubing it. I could say G of Bob equals Bob cubed. It would serve the same purpose, right? So I'm just going to use a different dummy variable Y, and having done so, now, with no confusion of variables, I am, in effect, by saying G is going to be a function of Y, I am, in effect, saying I would like to view the outputs from F as being Y. Right? And now that there's no confusion of variables, the calculation is, there is no landmine. You can just, blindly, clumsily go through this calculation now kind of however you want. For example, look at what we've got here. So super dangerously, I'm writing down G compose F prime equals G prime times F prime. Carelessly, right? Carefree. And let's see here. Well, G prime is 3y squared. Just taking the derivative. Right? F prime is 2x. Right? Taking the derivative. Multiplying, I get 6xy squared. Oh, well that's weird. G compose F is a function of x. My answer has this y in it. What am I going to do about that y? This y, of course. Whoop, I missed. This y is the output from the f function. It's x squared. Yeah. Everybody see what happens? And so you can't mess it up. Unless you just downright try to mess it up. The choice of having avoided the dummy variable, right? There is no landmine to step on. The choice of variables has reminded us how to avoid stepping on a landmine. Okay. All right, so this is, like I say, this is all single variable calculus, flashback to a long time ago. The point is that the same situation comes up in a multivariable context, and it's arguably more sort of notationally dangerous in the multivariable context. So here's a pair of multivariable functions, both from R2 to R2. You can compute those Jacobian matrices. You can then ask what's the Jacobian for the composition, and you think, chain rule. I'm going to take these individual Jacobians and I'm going to multiply them, because that's what the chain rule is. Which is, if you're not careful, you're going to end up doing this, which of course is wrong. Right? So don't do a confusion of variables thing. Just avoid the confusion of variables entirely. Right, so here's the wrong way of doing it. Let's avoid that entirely by just rewriting G. There's that same function G, now written as a function of not x and y, new variables. I've made up two new variables, u and v. Pulled them out of a hat. Notice that as is required, the things that go into G are the things that come out of F. Right? So when I choose this new dummy variable, I'm choosing u and v as my dummy variables. That tells me formulas for what u and v are. They're functions of x and y as given by f. And then again, you know, it's all you're all good. You know, plug and chug at this point. So multiply the two Jacobians. Notice that the u and the v. You know, what is that u right there that came up in the Jacobian of g? Well, that u is what it has to be from the f function. And this v right there is what it has to be. And then you know, you got to multiply this out. Yeah, everybody see that resolution there? Oh, just avoid the confusion of variables and everything's fine. Okay. Alrighty, let's talk about second derivatives. Doing second derivatives with the chain rule is it's a little weird. I mean, gosh, it ends up being that in the multivariable setting, there's a technique that is just more important to be aware of and to have at your disposal than in single variable. In single variable, if you want to take a second derivative with the chain rule, go ahead. Just take one derivative with the chain rule, compute it all out, and then when you're done, take another derivative with the chain rule. I mean, there's no need to have a sort of a more sophisticated point of view on it. So what I want to start with is, again, you know, with the single variable chain rule, let's ask, well, what would a second derivative chain rule look like? Here we go. Here's a single variable composition. Y is a function of x, z is a function of y. Here's the chain rule. Boring. Right, let me rewrite with this notation. You all recall this is an alternative notation to represent partial derivatives. Subscripts, right? This is, you know, on top here, this is kind of Leibniz-like, and down here, this is kind of Newton-like notation. It ends up being really handy. The Leibniz notation is pretty clunky, especially when we have big equations that we're about to have. And so this is just much more compact. It's really nice. Okay, so we're going to be using this notation largely going forward, so make sure you're comfortable. So z sub x means partial of z with respect to x, or derivative in this case. Okay, so let's talk about this thing, zy. And what is that thing? Is that a variable? Is it a function? What's it a function of? I'm just thinking this through. If you have z that's given us a function of y, z is some expression that involves a bunch of y's. Right? It's an expression of y. If you take an expression of y and take the derivative with respect to y, you get another expression in terms of y. So I propose that this zy, we should think of that as being a function of y, because it is. Right? And I'm going to append the diagram accordingly. Right? Here was our original little diagram showing z is a function of y is a function of x. Well, now we have this thing zy, also a function of y. If we're going to be taking another derivative, we need to have it indicated where is this thing and what is it a function of. Okay, likewise, yx is a function of x. Okay, so we have a new diagram to work with. And now let's take our next derivative. That was the first derivative. That's our first derivative chain rule. Right? If I want to take an x derivative of that, thus to give the second derivative of z with respect to x. Well, here we go. First, notice I'm taking a derivative of a product. Here's the product rule. Everybody happy? Haven't really done anything yet. Okay, now here's where we have to use the chain rule. Let's look at this factor here. This says derivative of zy with respect to x. And notice, you can see right here from the diagram, think these diagrams are really useful. I'm a big fan. Please use them. It's going to save you, if not mistakes, it's certainly going to save you confusion. So thankfully we have this diagram. We can see right here that, okay, so this derivative of zy with respect to x, it is the derivative of a composition. And so in order to make sense out of this expression, we have to use the chain rule to simplify that out. Okay. Now, we're going to use the chain rule. Conveniently, there's only one intermediate variable. The intermediate variable is just y. And so I'm going to have the partial of zy with respect to y times the partial of the derivative of y with respect to x. So all I've done here is use the chain rule to work out that derivative. Everybody on board with that? Just chain rule. And then there's just a little bit of simplifying to be done. It's all kind of, all the hard parts over. Notice that that's y sub x. I'm already multiplying by a different factor of y sub x. That's why there's a yx squared there. Here I'm taking the second derivative. Well, I'm taking the derivative of z with respect to y, and then I'm taking another derivative with respect to y. That's just a second derivative, so that's zyy. Right. And altogether then, there's your second derivative chain rule that I'll bet you dollars to donuts you've never seen before, because my gosh, why would anyone do it this way? How weird. Who needs this rule? If I need to take a second derivative, I'll just take a derivative and do it again. Okay. So anyway, this process though is a lot more valuable in a multivariable context than it is in a single variable context. I just wanted to start in the single variable context as a kind of a, to get the ball rolling. So here's the multivariable sort of equivalent. Right? By the way, this is a classical first example. It's everyone's first example in this this situation. So we have z as a function of x and y, multivariable function, right? And now let's note that, well, x and y are functions of r and theta per the usual polar coordinates formula. So in fact, we have a composition here. If you want to think of, if you have some function of position, not rare, right? Z is a function of x and y. If you want to re-evaluate that function and think about it in polar coordinates, again, not rare. Okay. This is the scenario that you're considering. By the way, there is a highly analogous scenario where you have some function of x, y, and z. So a three-dimensional domain. And then you might want to do it in terms of spherical coordinates. Right? And this comes up a lot in physics. If any of y'all are physics majors or engineering majors, I spent a bunch of time when I was y'all's age doing calculations on various different things. Quantum mechanics is one where this comes up a lot because you have a nucleus and an atom, and you're thinking about the wave equation of the electron, and so you're looking at functions in space that are very spherically natural and that are very important to think of from the point of view of spherical coordinates. And so this exact scenario of some function of x, y, and z, and then re-evaluating that in spherical coordinates, super common. Comes up all the time. Very important. Okay, so we're just going to do the polar version because it's a little bit less hairy. Only 2 variables instead of 3. Okay, so this scenario, let's ask the question, what is the partial of z with respect to r? Well, there's z, there's r. We have 2 intermediate variables. Yeah? Okay. And here are those terms. I don't mean cancellation by those slashes. I just wanted to point out that the x's and the y's you can see where these intermediate variables are giving rise to these 2 terms. So I'm not suggesting a cancellation there. In fact, just to emphasize, let me do it more like this. Those aren't slashes; those are just colors. Okay. Oh, and good news, I know the partial of x with respect to r. Right? I mean, that's a standard thing. X is r cosine theta, so that xr partial is cosine theta. Boom. likewise. Okay, similarly, if you want to take the partial of z with respect to theta, well, there's z, there's theta. You have two intermediate variables, x and y. And again, there, and you can rewrite details. I'll let y'all look. Okay, but let's do a second partial now. So I want to ask the question, what's the second partial with respect to r? So I'm going to come up to this equation that I just got that gives the first partial of z with respect to r, and I would like to take an r partial of this. So I'm going to be taking derivatives with respect to r of this stuff. Wait a minute. What is zx? How is zx a function of r? Where is it on my diagram? I don't see it on this diagram. We need to append this diagram to show how does zx fit in on this diagram. How does zy fit in on that diagram? As we've previously discussed, if z is a function of x and y, just imagine some expression involving x's and y's. If you have some big expression involving x's and y's and you take a derivative with respect to x, you're going to get a different expression in terms of x's and y's. Right? So this thing, like z, is a function of x and y. And likewise, this is a function of x and y. So I append the diagram accordingly. All right? I'm a big believer in this. I urge you to do this. It's very helpful when you're moving on to the next step. So here we go. Second derivative is the derivative of zr that we computed on the previous page. Okay. Now, first step, just product rule. That term has two factors. Since we write out the product rule, we get this. Just the product rule. Likewise, this term has two factors. Product rule gives me that. Everybody happy? Do notice, very conveniently, some of these terms disappear. What is the partial of cosine theta with respect to r? Well, theta is there, and the partial with respect to r, keep in mind when you're saying partial derivative with respect to r, what that means is we're going to consider r to be the only variable. We're going to hold everything else constant. Oh, wait a minute. That means we're holding theta constant. Theta is an independent variable. Partial with respect to r means that the independent variable is held constant. So if theta is constant, that means cosine theta is constant. We're taking the derivative of a constant here. This is 0. Right? Everybody happy? It's kind of like, when we were first talking about partial derivatives, and we made the observation that the partial of, like a y cubed cosine of e to the y, with respect to z, is 0. Because this is a great big nasty function of something that is being held constant for the purposes of this derivative. Same deal here. Right, so this is 0. That means that this whole factor goes away. Likewise, this whole factor goes away, and we're left only with these two terms. That term and that term. Yeah, everybody good? Questions? Feel free. Okay, now here's where we have to worry about the chain rule again. Look at this guy here, partial of zx with respect to r. Do we need to look at the diagram? What does that mean? Can I, how do I deal with that? Well, here's zx. Here's r. There are two intermediate variables. That means that we're going to apply the chain rule. We're going to get two terms, one term for each of the two intermediate variables. Partial of zx with respect to r. By the chain rule. First will be zx with respect to x, then x with respect to r. That's the first term, first intermediate variable. Then zx with respect to y, and y with respect to r. That's the second term. Pretty good? And then it's all bookkeeping from there. Well, likewise with the partial of zy with respect to r. Again, there's two intermediate variables. Again, you get two terms. After having done all that, it's bookkeeping. It's a matter of sort of multiplying everything out. Here, this is clearly just a second partial with respect to x. Partial of x with respect to r is cosine theta. Old news. Blah blah blah. With this. Okay. So if again, you find yourself looking at some function z that's a function of x and y, some function of position in the plane, super common scenario, and you say, hey, I'd like to think of that in polar coordinates. What does it mean? Take a second derivative in polar coordinates of this function that's actually given in terms of x's and y's. Boom, formula. Very handy. Comes up a lot in physics. Okay, moving along now to the next section. This is a relatively short section, so I think we've got a good chance of getting this done in our remaining 14 minutes. We'll see what might be possible. Implicit differentiation. I'm going to spend a certain amount of time talking about something y'all have already seen. Y'all have already seen implicit differentiation. It's a standard topic in Calc 1. Right? So specifically, how would you find, let's say, the slope of that tangent line to this curve, that circle of radius 5 centered at the origin, at the point 3, 4, how would you find the slope of that tangent line? And of course, the knee-jerk reaction would say, oh, did somebody say slope of a tangent line? Isn't that just the derivative? Right? You gotta be careful. Slope of a tangent line to a graph of a function is the derivative of that function. This is not the graph of a function at all, much less a function that we know. Right? So this curve here, you might write this as x squared plus y squared is equal to 25. That is not writing this curve as a graph. This does not say y equals. It doesn't. It's a level set of this function, right? But again, it's catastrophically not okay to just say, derivative of, the function. It's a curve. So just, take the function, whatever function. And derivatives or slopes. Doesn't work at all. It makes no sense at all. Okay. So, again, big problem. This is not only is it not a graph of a function we can write down, it's not a graph at all. This fails the vertical line test. So it's really not a function at all. I can kind of fix that problem by pointing out that, well, look, I can just, fine. Okay, if you want to know the slope of this tangent line, to that curve, I argue that, it's the same as the slope of the tangent line to that curve. I don't really need the rest of the circle. I can look just at that purple part of the curve, and curve as far as the vicinity of that point is concerned. It's going to give you the same tangent line. It's going to answer the question. And this purple curve, very conveniently, is a graph. It passes the vertical line test. It's flying colors. So so you can kind of bypass the problem of it's not a graph by just restricting your attention to a certain part of the curve. All right, now that being said, what is this part of the curve the graph of? Well, this is a graph of y as a function of x. Now, I would like to emphasize that I do not yet know y is a function of x. And I know what you're thinking. You're thinking, okay, well, yeah, but you could do that. Come on, you can solve in this algebra. You can take x squared plus y squared equals 25. You could totally solve for y in there. We've already decided right here very clearly that we want y to be positive. We've thrown away the part where y is negative. So I could literally write down a formula for y. And I suppose you could. The idea here, though, is we want to talk about implicit differentiation. I want to talk about how to find derivatives I want to find the derivative of this function y without having it explicitly as a function. If I could find y explicitly, I wouldn't need implicit differentiation at all, right? So let's consider the scenario. Let's pretend that I can't solve for y. I just don't know how to do that, because that situation will arise plenty, and that's the situation in which we need an implicit differentiation at all. Okay. So how do we proceed? And the way we proceed. By the way, let me recognize that I have already committed a little crime, a little oversight at least, and I'm going to come back and fix that later. But I want to talk about the method first. And here's the idea. We have x squared plus y squared is 25. I want to recognize this as a composition. So I'm viewing y as a function of x, right? So y is a function of x, you see right there. And that's what I'm going to plug into an equation that gives me the curve. You know, the equation of the curve, y is an input to the equation of the curve. Right, so altogether, x squared plus this function, y of x squared, is 25. Viewed as a composition, this is just now a great big function of x, and I can use the chain rule. Of course, derivative of x squared is 2x. It's boring. Here's the chain rule. Taking the derivative of y squared, but I'm taking the derivative of y squared with respect to x. So first I take the derivative with respect to y, that gives me 2y. Then I multiply by dy dx, that's y prime. Talk one. Derivative of 25 is 0 because 25 is constant. And this is not what I'm looking for. So I took a derivative, admittedly, right? But I took a derivative of an equation. I did not take a derivative of the function y. I took a derivative of an equation involving y. So I don't yet have the answer that I'm looking for, but the answer that I'm looking for has at least showed up. And so now you can just solve for the thing that you want. I just made the mistake of looking right into the bulb there, so I'm having vision problems there. I'm sorry. Hopefully my eyes will come back in a moment. Man, that is hard. Okay, so you can solve for that y prime, and you get this formula here. Okay. All right, the compact way that y'all saw it, writing this down in high school. This is the compact way to do it. That's the equation for the circle. Take the derivative with respect to x. Solve for the y prime. Plug in the point in question. Right, and there's your answer. Okay. All right, is everybody on board so far? Hope this looks familiar. Has everybody seen this before, I presume? Okay, great. Cool. So let me tell you the crime that I committed. Like I say, a crime. I made an assumption for which I gave no justification, and furthermore, my assumption is something that's not always true, and I could have gotten in big trouble here, and I got lucky and didn't. But I could have gotten in big trouble, and this could have been complete garbage. And it's only good fortune that protected me. So here's what I assumed. I assumed that at this point, it was true that I could take the curve and ignore a large chunk of it and look only at a sub-portion of that curve and erase the rest, and that what would result would, in fact, actually pass the vertical line test. Now, that happens to be true here. But it is not always true. Check out this point. Now, that's the same curve. Right, this is still the curve x squared plus y squared equals 25. Same exact curve. If we consider this point, where y is equal to 0, x equals 5, y equals 0. At that point, if you say, look, I don't need the whole curve, I'm just going to restrict my attention to just a part of the curve there. I'll throw away the rest of it. This does not pass the vertical line test. It doesn't. right? No matter how little curve you keep, no matter how small of a little curve here you restrict your attention to, there will always be some vertical line that intersects it twice. Because the curve at this point is at that instant in the process of wrapping under itself, and it's just, it doesn't matter how much you erase, there's always a little bit wrapping under, and it's always going to fail the vertical line test. So now, why is that a problem? Well, it's a problem because the very first thing that I did after saying, hey, look at this, I can treat this as a function, is I declared y to be a function of x. Namely, the kind of thing that I am allowed to take derivatives of. If that's not true, then this is garbage. In fact, this is garbage. If y is not a function of x, right, then none of this makes any sense. Right? So in this scenario here, if I were to say, okay, well, on that curve, let's let y equal y of x, the proper response would be, no, you can't say y is a function of x. It isn't. It's really not a function of x. Okay. So the whole thing comes crashing down. So how do we deal with this? And we have a theorem that's going to allow us to bypass this problem most of the time. So I'm going to consider our original equation. By the way, keep in mind every equation can always be written as something equals 0. Right? And whatever equation you have, if you've got stuff on both sides of the equation, take the stuff on the right, just put a minus sign, throw it over to the left. Now you've got stuff equals 0. So let's do that. Turns out that this function is going to be very important in this process. And I want to start by emphasizing this is not the same function as the function y. Y is a very different function. So y says, locally on the curve, how is y a function of x? F is a function of two input variables. Right? That says, how do x and y together combine in such a way to make this equation always be satisfied. So it's very different. Here's another way to say it. F and y are different in that the curve is a level set of f, right? But at least locally, it's the graph of y. So remember, these are two different, the level set construction, the graph construction are different constructions. Both of these functions, f and y, they do relate to the same curve, but they relate to that curve in these very different ways by way of these different constructions. Okay. All right. So, that in mind, let's look at this picture. Here's a scenario that we're most afraid of. We're afraid of this point here because, oh man, the curve is in the process of wrapping under itself. And no matter how much of this curve I erase, if I'm interested in what's happening at that point, no matter how much of the curve I erase, I am in trouble because there's going to be a vertical line that intersects that little, no matter how small that piece of curve is, a vertical line will intersect it twice. Okay. Whereas, on the other hand, a point like this, I'm not afraid of that point. The original curve that I have, I can erase a bunch of it. Now I got to make sure to erase enough. If I erase all but that, I have not erased enough. I've got to make sure to erase enough so that, again, it passes the vertical line test. Okay. All right. So now how do I distinguish between these two cases? And I claim there's something pretty geometrically natural going on here. The fact that this is in the process of wrapping under itself, I can detect by the fact that there is a vertical tangent line. Now, some of y'all might be thinking, oh, doesn't that mean the derivative equals infinity? No. Derivative of what? There is no function. There is no function whose derivative is infinity. Right? So please, please, please do not think of this as, oh, the derivative is infinite. There is no derivative to talk about. Right? So vertical tangent line, though, we can say. And keep in mind, vertical tangent lines, if you think about it, if you have a vertical tangent line, that means vertical tangent line, that means that the gradient, which is always perpendicular to that, I'll write that in a different color, the gradient, which is always perpendicular, must be horizontal. Right? The gradient is always perpendicular to the level set. So if a level set has a vertical tangent line, the gradient must be horizontal. Keep in mind that this gradient has easy formula. It's partial of f with respect to x, partial of f with respect to y. So if this is horizontal, that means that that is 0. Horizontal means no second component. That means that that second component is 0. Okay, so roughly speaking, here's what we've proved. If there is a problem, colors. If there is a problem, and that implies that the partial of f with respect to y must equal to 0. And the way we're going to very conveniently turn this around then is called the contrapositive. This is a logical construction. If the partial of f with respect to y is not 0, then no problem. Right. So if P implies Q, not Q means definitely not P, right? I mean, just imagine if there was a problem. If partial of f with respect to y was non-zero and there was a problem, that problem meaning that it partial is 0, but wait a second, we just said it wasn't 0, impossible. Right? So what this gives us is a tool for ensuring that we're okay. If you take the partial of this function f with respect to y, if you confirm that it's not 0, you're good. Feel free to go ahead and view y as a function of x. It is. Everything's fine, and go about your business. And so here's that theorem, and here's an example of how we use it. Now this is the same example that we just saw with the circle, right? But this is now what I feel like is an appropriately proper treatment of the matter. We have that equation. Want to know what's the slope of the tangent line? I would like to just go ahead and start treating y like it's a function, but I have to be really careful. I don't want to just assert something that's not true. And so I take the partial of this function, take the partial with respect to y, I get 2y, into which I plug that point, I get not 0. Right, so here's your f. Partial of f with respect to y is 2y. Plug in the point, you get 8. 8 is not 0. Our theorem tells us that means that this is not a problem. Y is a function of x. And then all of this is just fine and dandy. Okay, all right. I'm sorry, I lost track of time. Went a couple minutes over. We're not quite done with this section, so I'm not going to assign this section for today. For today's homework. So today it'll be just the chain rule section 4.9, and I owe y'all an email to that effect. And yeah, see y'all later. Have a good weekend.